presentation. Before I introduce Alan Shapiro, Director on the Scientists and Engineers Division Board, I would like to remind you that for this presentation and for the McElhaney presentation in here at 3:30, we'd appreciate it if you would get scanned in and out by our students over there. We're trying a pilot project, and we really need your cooperation with that. So if you get a buddy who comes in afterwards or leaves earlier, please remind them about that. So without further delay, Alan, if you would come up, please.
Good afternoon. My name is Alan Shapiro. I'm with the U.S. Geological Survey, and I'm also a board member of the Scientists and Engineers Division of NGWA. And I have the great pleasure of introducing the 2012 Distinguished Darcy Lecturer, Dr. S. Majid Hassanizadeh. Before I extend a plaque to Majid and another token of appreciation for his lecture series this year, let me give a little background about the Darcy Lecture Series for those who may not know about it. The Darcy Lecture Series is supported by the National Groundwater Association Research and Education Foundation, and it is probably one of the most highly visible lecture series in groundwater science that we have on a yearly basis. It is one of the most sought after, he is one of the most sought after lecturers. Universities, research institutes, even private companies are clamoring to get this person to give a lecture. So this is highly visible, and it is indeed an honor that someone like Majid receives this. In many instances, the topics that these lecturers talk about are going to be the next hot topic that will be of concern to the groundwater industry. And I think what Majid is going to talk about today, I can't guarantee it, but you will probably be hearing about this in the future. So this kind of gives you a precursor of what the next wave will be in the groundwater industry. I'd also like to point out that the Darcy Lecture Series is not an easy task. And I think, you're catching Majid at the end of his lecture series, and I'm sure he's probably glad maybe a little bit glad that this is over, because this is an arduous task. He has delivered a lecture at close to 50 locations. He has traveled to, by my calculations, about 13 countries, which also speaks to the importance, the international importance of these topics. We are here at a national meeting, but the things that he's talking about, the issues that we're dealing with in the groundwater industry are not local to our country, they're international. And that is very important. That's very important for the private sector and research as well. Okay. I'd also like to point out that he's given this lecture at over 50 locations, but he's probably received 2 or 3 times that number of requests. So I think if you've seen him during the year, you were lucky to get on his schedule. So let me tell you a little bit about Dr. Hassanizadeh. First of all, it is little known fact that we were in graduate school together. So it is a pleasure to see him again. He hasn't changed in 30 plus years. So Majid is a professor of hydrogeology at Utrecht University in the Netherlands. He has been involved in private consulting, and he's been affiliated with high-profile universities, both as a faculty member and a visiting professor at these universities, which include Delft, Stuttgart. He's also been a visitor at the University of Notre Dame, which is renowned for their civil engineering program. And I think they also have a pretty good football team, too. Dr. Hassanizadeh has been prolific in his writing about his research and delivering lectures over the past years. He has also served as an editor of numerous high-profile journals. And his research, he is renowned. He's absolutely, when you think about this area of research, you think about him. He is renowned for his ability to capture and explain fundamental phenomena in groundwater flow, chemical transport, transport of colloids, transport of viruses, from the building blocks, from the underlying structure of porous media. When you think about this topic, you think about him. He has accomplished this through a series of theoretical investigations, through laboratory experiments, and through field investigations, which is, to have someone involved in that entire gambit is unique in our field. So with that rather lengthy introduction, I'd like to present a plaque to Dr. Hassanizadeh, recognizing his contribution to groundwater science and recognizing his Darcy Lecture Series. So, Majid.
Thank you very much.
Okay.
Thanks a lot.
Okay. I have one more item of business here before I'll turn the podium over to Majid. Also, as part of a lecture series, NGWA provides the lecturer with a book, which is the translation of Henry Darcy's publication, The Public Fountains of the City of Dijon. So this is a translation, and I received one, and I hope you read through this yourself.
Thank you so
very
much.
much.
I really appreciate it. Thank you. I need to have this. Okay, great. Well, thank you very much, Al, for such a generous introduction. It's my great pleasure to be here at the NGWA annual meeting. I always wanted, it was a dream for me to give a lecture about my work, what I really is my passion at such a high-profile meeting. Let me see, I just used the, or is there a remote control for the, okay, I'm going to use this. So as you know, this lecture series is indeed instituted by the National Groundwater Research and Educational Foundation, which has many other activities, and I would like to once again invite you to visit the website of the National Groundwater Association. What I talk about is an overview of the work that we have done during the last 15 years related to movement of viruses in the subsurface and using that for cleaning up water from pathogenic microorganisms. So I would like to acknowledge my collaborators, former PhD students, the first three, and two current PhD students, and a colleague from the Utrecht University. Why should we be interested in modeling transport of virus in the subsurface? I'm going to give you a few examples. The first one is from the Netherlands. 1/3 of the drinking water in the Netherlands comes from surface water sources. And surface water sources are always contaminated with pathogenic microorganisms. And these are typically taken care of, disinfected, by chlorination, almost everywhere. Now, that is not allowed in Holland for a few reasons. And one reason is that there is an alternative. And the alternative is called dune infiltration. The idea is that surface water, after some pre-treatment, is put into canals that are in dune sands. I'll show an aerial photo in a minute. They put them into these canals that are dig in dune sands, and then they are about 100 to 120 meters apart. And in the middle, there is a row of wells, And when the water comes out of these wells is actually the water that was put into the canals, traveled horizontally for about 50, 60 meters, and this will get rid of the microorganisms. How that works, I'll tell you in a minute. About half of that surface water is treated in this fashion, and that is 1/6 of the drinking water in the Netherlands. Here is an aerial photo of one of 14 sites. These are all constructed in the dune sands along the North Sea coast of the Netherlands. As I said, we have these canals, parallel almost, and then there are more of them here, and then there are a row of wells in the middle that withdraws that water. Now, what is the efficiency of such a system? Well, the surface water has typically anywhere from 20 to 10,000 microorganisms per liter. If you take Rhine water on a typical day, it will have 100 microorganisms per liter. During pre-treatment, this is like coagulation and sedimentation. About 90 to 99% of this will be removed, and that means from that 100, we are left with 1 virus per liter. Now, some of you may think, well, that's not too bad. We should be able to handle that and drink that water. We should not. We must not. That is too much. You will get sick. Now, there is, of course, not possible to guarantee that no one will ever get sick as a result of drinking water. There's always a possibility and a probability associated with that. So there is a regulation that says that the allowable risk of infection from drinking a couple of liters of uncooked water per day is that 1% out of 10,000 people can get sick once a year. And this has been translated, calculated through risk assessment to a concentration. And that is a concentration of 2 times 10 to the minus 4 viruses per cubic meter, which is 1 virus in 5 million liters. So that 1 virus per liter, that's 5 million times too much. And that has to be reduced by that factor. And because we are working with these very large factors of removal, we have a unit called log removal, unit removal of log. And 1 log removal is equivalent to 90% removal. 2 log removal is 99% removal. And we need 6 log removal. That is 99.999 and some more 9%. That is what we have to achieve. And this is achieved through dune infiltration. I will talk about that in a minute. Other examples, sometimes the surface water, instead of putting into these shallow canals, we simply use them for replenishing deeper aquifers, so they are injected into deeper wells. If even the source of drinking water is groundwater and not surface water, we still have to study and model the movement of viruses in the subsurface. And the reason is that the groundwater wells in the Netherlands are often in shallow groundwater systems, often unconfined, sandy soils, so they have to be protected on the surface. There is a protection zone around the groundwater wells, and within that protection zone, no sewage lines are allowed, no animal husbandry, no settlement. But at the border, you can have a sewage line, and that could be, it is leaking. And then we have to ensure and determine that that will not reach the microorganism from there, will not reach the groundwater well. Sometimes instead of taking the water directly from the river, we take it from the bank of the river. At a distance of 100 to a couple of 100 meters from the river, we put wells and we draw the water, and that water is coming from the river, passing through the banks of it. And this will also take care of the pathogenic microorganisms. We talk a lot nowadays, and sometimes it is being done at some places, to use treated or untreated wastewater for agricultural purposes. And the viruses there will seep down to the groundwater table, and we need to know about the fate of them. Also, septic tank effluents, they are typically discharged into canals or into pipes that are installed in the unsaturated zone horizontally, and there again they seep down to the groundwater table. And finally, in many parts of the world, there is no sewage system. Under the buildings, there are dry wells if the groundwater table is low, and the wastewater from the building goes directly into those wells, and again seeps down to the groundwater. And in many smaller cities and in villages, there is actually a drinking water well in the yard, only 5 meters or 10 meters away from such a sewage well. And often that goes okay too, because of the ability of the subsurface for removing viruses. So we need to model, for these reasons, the movement of viruses in the subsurface. Processes that we are interested in are advection, dispersion. Now, these are well-known processes. We study them in this relation to many other solid transport processes. Two very important processes related to this virus removal are attachment, detachment, which you can also call them adsorption, desorption, and inactivation. Inactivation relates to the fact that viruses are eaten up by protozoa and bacteria that are in the water. They're food for them. In addition to that, their protein capsid can disintegrate and they will not be active anymore. Or the DNA in their nucleus will get damaged and they will not be active, they will not be infective anymore. That's why we call it inactivation. So they will actually be gotten rid of in various mechanisms that we collectively call it inactivation or die off. Viruses do not grow by themselves, as you may know. They always need a host to grow and to multiply. Pathogenic viruses that are of interest to us, they have as host either human beings or animals or plants. And these hosts are not present in the subsurface. So we usually don't need to worry about the growth of pathogenic microviruses in the subsurface. Whatever we learn from studies of these processes are also useful for other reactive transport problems and for colloid transport. And the other way around, we learn from the study of colloid transport to infer information about virus transport. Now, one thing about modeling, there are many consulting companies, even colleagues at universities, and people from the government agencies that they don't believe in modeling. They say, your models are never come out, the system is very complex, there is heterogeneities, there is this, that, and we don't need modeling. We are producing drinking water. You're worried about something in there, we measure it. You worry about there is PCE in there, we measure pictograms per liter. And then we can show it's clean. Therefore, we don't need modeling. No, they cannot say that about viruses. Because, as I told you, what is allowable in drinking water is one virus in 5 million liters. You cannot measure that. The best we can do is to measure one virus in 1,000 liters. And that is the limit of detectability. You take that 1,000 liters of water, we have to do microfiltration, superfiltration to capture that one virus in there if we can, and that's the best we can do. So if they can show there is measure and they find one virus in 1,000 liters, that's 5,000 times too much. So the only way you can provide assurances and do safety assessment for these drinking water systems is modeling. I hope modelers are happy with that. I'm really happy about that. Now, the research question, therefore issues that we need to answer in setting up models for virus transport is the adsorption, desorption. How do we model that? Is that equilibrium process or is it kinetic? Equilibrium, is it one first order, higher order? If it is kinetic, is it one-side kinetic or two-side kinetic? I'll explain that in a minute. What is the influence of hydrochemical conditions like pH, ionic strength, calcium, phosphate, organic carbon, and temperature on this removal process? And what is the effect of water content? I'll explain later why this would be important, the soil moisture content. And finally, the effect of transient conditions. We usually deal with steady state conditions, but what if the chemical or hydraulic conditions change all of the sudden. So this is basically what is here, actually, the outline of my talk, because I will give you a report on a field experiments we did, and then I'll look at the influence of pH, ionic strength, calcium, moisture content, and transient conditions on the removal of viruses in the soil. One disclaimer is that I will tell you, in our studies, field or lab studies, we did this with viruses and we measured this and that. Actually, we don't use any viruses in our studies, not pathogenic viruses. We use what we call model viruses. And the reason is that, as I told you, we are dealing with large factors of removal, 10 to the 6 per liter. And if we want to measure that in a field experiment, then we should also put a large number of viruses seed in there in order to measure them. Now, no water company will let you put in one virus in the subsurface, let alone 10 to the 6 per liter. So we cannot do that, and therefore, also in the lab, we cannot use pathogenic viruses easily. You need a certified lab, you need trained personnel. A lot of our research is done by MSc student and PhD student. Now, you cannot send the MSc student into the lab and say, go and play with poliovirus, for example. Okay, so we have to work with these, what we call model viruses. These are bacteriophages, and these act as surrogates for pathogenic microorganisms. By learning their behavior, then we infer information about the behavior of pathogenic microorganisms. They are called bacteriophages because they are viruses to bacteria. And these are, for each of these bacteriophages, is very specific bacterium host that is not present in nature, so we don't worry about them growing and not having a controlled experiment. We have them in the lab, and actually we use these hosts for culturing and counting the number of viruses in water samples we take. They should be harmless to a human being, and they should have properties similar to pathogenic viruses. In fact, when we use them for field experiment, we want them to be less conservative than pathogenic viruses. So we do actually experiments in the lab involving both pathogenic and model viruses, compare them to each other to ensure that they are good model viruses. Here are some examples. MS2, this is a portrait photo. The size, 26 nanometer. Viruses are anywhere from 20 to 70 nanometer in size. They are not large. And these are two very important properties, isoelectric point and hydrophobicity. As I told you, one of the major processes is adsorption. Now, one of the mechanisms of adsorption are electrostatic interactions between the virus and the soil grain. Now, if the soil grain, when we are talking about sand, it's quartz, is usually negatively charged. Under the pH conditions we have, they are negatively charged surfaces. So if this virus has a negative charged surface or a positive charged surface, it makes a huge difference in terms of adsorption. But the surface charge of these viruses is not a given constant. Actually, it's variable, and it depends on the pH of the solution. And there is a pH, in this case, pH of 3.9, at which there is zero charge on the surface. It's a neutral charge. Above that pH, we will have negatively charged surface. And below that pH, we'll have positively charged surface. So this is very important. And hydrophobicity is important because adsorption means that the virus leaves water to go and sit on the sand grain. And hydrophilic viruses don't like to leave water, whereas hydrophobic or partially hydrophobic would like to do that. So this will also affect the strength of adsorption. Another virus, PRD1, this is the size, 62 nanometer. Otherwise, so it's bigger virus. Otherwise, the properties are more or less the same as MS2. We have more viruses. I mean, we have actually quite a number of bacteriophages, and depending on the kind of pathogenic virus we want to study, we use one of these. Here's another one, FX174, and this is a smaller virus, but it has a very high or relatively high isoelectric point, 6.6. This is very important because groundwater systems are, their pH is somewhere between 6 and 8. So if the groundwater pH is 6, this will be positively charged. And that makes a huge difference in terms of the adsorption ability and strength. And it is hydrophilic, which means that actually this one doesn't like to leave water, and therefore in that sense this would be less strongly adsorbed. So we have a combination of these. And in fact, I will show you later in my presentation why is it that we see a range of behaviors from viruses, because it all depends on the conditions that are prevailing. Here is a canal from that field site, the aerial photo I showed you. I'm going to tell you about this field study that we did. We used this is sheet piling. By sheet piling, we separated this part from the rest of the canal, but the flow of water is simply continuing. And then we use this as our seeding reservoir. And we use MS2 and PRD1 as the phages, as the model viruses. We also use salt. We didn't do that simultaneously, I must say. We use salt in order to, as a tracer, in order to determine hydraulic properties of the soil, the flow velocity and dispersivity and so forth. Now, here is a plan view of the system. So that is the canal. This is the part that was separated. And along this transect, going to this water production well, they are a row in here. We put a number of boreholes in order to sample water and monitor the concentration of viruses. If you look at the cross-section of this along this transect, you see that what the numbers we are showing here for hydraulic conductivity, that the hydraulic conductivity is not very variable. I mean, the factor T is not much. And this is very homogeneous sand. And this is extremely important for this system to work. Because if instead of this being sand, we had here a lens of gravel, for example, that would work as a highway that will take viruses from the canal to the groundwater well, and then 60 meters will be by far not enough. So in fact, if you have a fractured system, for example, this will never work. In fractured system, viruses can travel thousands of meters, and in a car system, it can travel 20 kilometers. So that's why this works here. We need clean, homogeneous, and say between fine and medium grain sand. Here are data from that field experiment. I'm showing you in blue circles the measured virus concentration at various wells away from the canals. These are the distances are given here. What we did, we seeded this PRD1 and MS2. These are, by the way, graphs for MS2. We seeded this into that reservoir, input reservoir, for 11 days. And after that, we discontinued and measured the breakthrough of viruses in these wells. As you can see, the concentration goes up, it stays high for about 11 days, and then it goes down. A couple of things you can see here. First of all, you see that after 10 meters, we put in here 100 million, 10 to the 8 viruses per liter, we seeded there. And you see that after 10 meters, only 10 to the 3 is the maximum. So this is already a log removal of 5, which is 100,000 times removal of the concentration. What you also notice is that these are days. It takes a long time for the viruses to come out of adsorption. Now, those who have done modeling of solute transport, they would recognize immediately this is a kinetic behavior. So this is kinetic adsorption. It's not equilibrium adsorption. That's why you have this very long tail. We modeled this, and the red curve I'm shown here is the result of our modeling simulation of these results. And you may say, oh, you really did a very good job. Not too bad. But actually, we were not quite satisfied. I'll tell you in a minute why not. Now, these are the equations we used. The porosity, concentration of viruses in water, dispersion term, advection term, This is inactivation. As I told you, the viruses are eaten up and die away, die off. And mu W, we model it as a first-order decay process. Mu W is the rate of inactivation of viruses in water. Then we have rate of absorption, and the rate of absorption means that viruses will adsorb to the soil, and this is the equation for adsorbed viruses, where rho B is the bulk density, CS, the concentration of adsorbed viruses. And adsorbed viruses are also eaten up by bacteria and protozoa and die off. So we also have a rate of the inactivation of adsorbed viruses with their own coefficient mu S. And this adsorption rate is modeled as a linear kinetic process. So we have two coefficients here. One is attachment coefficient, the other is detachment coefficient. So that's how we model the kinetic adsorption process with these two coefficients. We modeled this using Hydrus 1D, and as I said, we were not quite happy. Here is the reason. So the blue again is the measured data, and red is our simulation, and this is logarithmic. So you can see there is a very large discrepancy between results, the measurements and simulations, and we try to explain that, and our explanation is as follows. If you take a sand grain and you look at it, even with the naked eye, you will see different colors on that. The quartz is sort of yellowish, and that's the most part of it, but you can see red spots on there, or black spots. And a red spot is a metal oxide. And metal oxides are positively charged surfaces, whereas, as I said, quartz is negatively charged. So you can have stronger adsorption to that little spot compared to the bare quartz. Or the black spot could be organic matter deposited. And that will also have a different adsorption behavior. So even on a single sand grain, you have different adsorption sites, and with their own rate of adsorption. So when you have a large number of sand grains and you have these spots, red spots there, you actually have to deal with two different adsorption sites with their own rates. So we modeled this as such. We went back to the equation, and now we have two different rates of adsorption related to the two sites. So their own concentration, their own attachment and detachment coefficients. So now we have these four coefficients. And with this, also using Hydrus, now we did a much better job. You see that now the red curve goes right through the measurements all the way, instead of the blue, which was the previous one. So we were happy, actually, but not the water company was not happy. So look, we don't want to deal with 4 adsorption and desorption coefficient, which actually don't even want to do adsorption experiments to determine the safety of the system that we have. Is it for this operation of 50 or 60 meter travel distance really necessary to do a two-site kinetic model? So we did some sensitivity, and we showed that, well, this second side, which is the strongly adsorbing side, is actually more important than the weakly adsorbing side. And the weakly adsorbing side gives you a better fit, but otherwise it's not really playing a major role for that whole travel distance. So one-side kinetic would be enough. Now, the water company also asked the following. They said, look, we can measure pH, ionic strength, calcium, the composition, organic carbon. We can measure that, but measuring attachment coefficient each time we are going to change something in our system, that's too much. Can you give us an indication of what these attachment coefficient will be if we give you pH and ionic strength and calcium and so forth? So we said, yeah, that's a good question. We know actually how pH, ionic strength affect these processes, but to quantify that and give you a formula, then we need to do more experiments. And now that means we had to do experiments in which we change pH and ionic strength, and that you cannot do in the field. Those are given, and you cannot change them in large factors. So we went to the lab and to look at the effect of these factors, and we did batch experiments as well as many batch experiments as well as column experiments. With the batch, we do it without sand. Then in these bottles, we put in viruses, and then we measure the change of concentration in each of these with time, and from that, we can calculate the inactivation rate coefficient. We can do that also with sand, and with sand, we also look at the adsorption behavior. We looked into the influence of water-sand ratio on our results, and also the influence of the mixing mechanism that we use in our batch experiment. For example, you can have mixing simply putting on a shaker, or you can use this system where we rotate the bottles of sand and water along the longitudinal axis, or we can have them tumble around in this fashion. And we showed that actually this could have an effect, which would be an artifact of your measurement on your results if you are not careful. I'll not talk about that. I'll talk about the column experiments we did. These are columns of 50 centimeter long, filled with clean quartz sand. We used, after, say, filling the column with sand and making sure that there is no air trapped in there, then we prepared a solution of given pH, given ionic strength. This was all done in the constant temperature room, so we could change the temperature from, say, 10 to 12 degrees. These are typical temperatures for the groundwater system. And so then once we have a pH and ionic strength fixed for a given solution, we put this solution through the column. We don't change it. We do it during the whole duration of experiment. We buffer pH and make sure that ionic strength remains constant. Then at some point, we put in the viruses. And we put that for a short duration, 1 pore volume. That's the time it takes for the virus to traverse the length of the column. And we use PRD1 in these experiments. And we did this then with a variety of combination of pH, ionic strength of calcium. And we also did experiments in which we did transient experiments. I'll explain that in a minute. So here are some results. This is at ionic strengths of 1 millimole at different pH, 4 different pH. There is not much really significant effect, although this is statistically significantly different enough to tell us that if you decrease pH, you have more removal, you have more adsorption. As I said, these are actually known results, qualitatively known results, and can be explained. If you go to higher ionic strength, now you have a lot more removal, and the effect of pH becomes even more significant. And we go to a higher ionic strength, 20 millimole, then you see that the effect is absolutely very large. As I said, these were known, but what we were trying to do here is to have sufficient data in order to develop an empirical formula that I'll show in a minute. So we wanted to calculate this attachment coefficient for these different conditions. But instead of working with attachment coefficient, we prefer to work with another coefficient called the sticking efficiency. And the reason is that attachment or adsorption coefficient is also a function of velocity, that is that V here, porosity, grain size distribution, diffusion coefficient, and so forth. This formula is coming from colloid filtration theory. And this is proposing that there is a coefficient called the sticking efficiency that is independent of those other properties, the velocity and so forth. So we calculate this alpha so that if conditions change, velocity or porosity, we can still use this alpha and then get attachment coefficient using this formula. So we calculated alpha, plotted that versus ionic strength and pH, and we fitted the formula to that, which actually is pretty simple formula, exponentially varying with ionic strength and pH. Alpha 0 depends on other factors and parameters. I'll show you in a minute what that could be as one major example. Now, the way we, by the way, fix the ionic strength is by dissolving sodium chloride in the water. But then the question came up, ionic strength could be also determined by calcium in addition to sodium. So is it important? What is making up that ionic strength? So I'm going to tell you about that in a minute. But one other thing about this equation is that this was obtained with this column experiment of 50 centimeter and with PRD1. And the question is this formula really valuable if you have other viruses or even you go to the field? So in order to answer that question, we decided to look into the literature, gather data as much as possible where they have either calculated attachment coefficient or alpha. The problem was that we wanted to have data in which they have reported velocity, temperature, pH, ionic strength, and grain size distribution. It's not easy to find published literature that has all of it. From those who we found, these are what we got. These are data from MS2 in a column, another bacteriophages lambda in a column, and PRD1, which is what we used under field conditions. They had calculated or measured themselves, and we calculated using our formula. If you plot them together and the formula is doing a good job, all those data points should fall on this 45-degree line. And in fact, you see that some of them do, and the rest cluster around this, which is telling us, at least in terms of order of magnitude, we have a formula that captures the main behavior and can be used for those assessment studies. As I said, we then went to say, okay, what is the effect of the makeup of this ionic strength? What if this ionic strength of 10 millimole is partly from sodium, partly from calcium? So we did experiments in which, first, this is without calcium, so only with sodium has been made, this 10 millimole. Then we prepared a solution where the calcium concentration was higher, and of course we had to reduce sodium concentration to ensure that 10 millimole ionic strength. And these are the results we got. You see that as the calcium concentration increases, 60 to 120 milligram per liter, you have much stronger adsorption and a lot more removal. So it shows you that we really don't have to have a formula not in terms of pH and ionic strength, but the formula in terms of pH, sodium, and calcium. By the way, if you just look at calcium, the sticking efficiency as a function of calcium shows a linear behavior. Now, one thing about this formula that I present here, this formula can be used only for interpolation. We cannot do extrapolation for conditions beyond outside what we did experiments with. And so when we now put all the data together, and I must say we are now doing additional experiments, different combination of ionic strength, calcium and sodium, we get this formula, which is alpha as a function of exponential, the function of pH, sodium concentration, and calcium concentration. If you ask why we chose calcium, because that's one of the major ions in the groundwater. And if you have the magnesium, will have a similar behavior as calcium. And other monovalent ions will have a similar behavior as sodium. One thing we did extra these experiments was the following. As I said, during these experiments, flow velocity and the composition was not changed. Except in these experiments, at some point, then we switched from this calcium solution of, say, 60 or 120 milligram to a calcium-free solution. It's still the same ionic strength by increasing the sodium chloride. And you see that we got a very large remobilization of viruses. If you had not done this, the viruses will come out just as in previous curves, as in here. They would come out slowly. But instead of that, when we change the composition, the calcium concentration, all of a sudden, you get a jump in the number of viruses coming out. And this is what we call remobilization. And this is very significant because in many systems, for example, if you are doing river bank filtration and there is a flood in the river, that is a huge change in, say, calcium concentration and other composition that all of a sudden occurs. And that is telling you that reduced calcium in the river water can remobilize viruses in the bank of the river that were actually up to now nicely adsorbed. This was all about saturated system. We are also interested in unsaturated system because many of the applications I mentioned in the beginning, the leakage from sewers and reuse of wastewater, they involve that the viruses will have to travel through the unsaturated zone to reach groundwater. So they move through the water in the unsaturated zone. Then the question is, would the water content affect this removal process? Now, the question is there a difference between adsorption to unsaturated and saturated media? I will explain that with these cartoons. The first, the one in the left is a cartoon of a saturated system, where we have solid grains and water, and the viruses, they can only adsorb to the surface of the solid grains. Moreover, the viruses that are in the middle, they cannot adsorb. They have to be next to the solid grain to get adsorbed. So that can happen by diffusion. So those who are in the middle, they will not see the solid surface. And therefore, the larger this pore size is, the less probability of adsorption we will have. Okay, now when we go to unsaturated, the pores are also filled up by air. And now you will see that the pore water thickness becomes much less than here because we have this air in there. So the viruses are forced to travel closer to the sand grain surface, and therefore a higher probability of adsorption. So under these conditions, you can have enhanced attachment to these solid grain surfaces, which we call solid water interface. Now, in addition to that, as I mentioned in the beginning, some of these viruses are hydrophobic. That means they don't like water. And one of the places they can go to leave water is this air-water interface. So they can stick to that air-water interface. At least on one side, they are not in contact with water. And they do that. And so this is another extra mechanism for adsorption, which we call attachment to air-water interface. And there is finally one extra special spot, and that is this spot like this one, where air and water and solid come together. We call that the contact line. There are other forces active there, and that can cause adsorption of viruses. And that, therefore, we can have attachment to air-water-solid contact line. So with all these three extra adsorption mechanisms, you would expect that everything else being the same, when the water content decreases, the adsorption must increase. And the question is that so? Now, one of the first people to do such an experiment were Wan and Wilson. Here I am plotting the concentration is normalized as a function of time or pore volume. And for three different situations, one is saturated with water, so 0% air, 15% air, and 46% air. Now, they have some removal when there is no air, but then when there is 15% air, there is more removal. And when there is 46% air, there is even more removal. So indeed, under unsaturated conditions, we will have more adsorption or removal. And the question is, which of the three mechanisms I mentioned are responsible for this extra removal? Now, the experiment they did was not actually with soil, and it was not even with viruses. It was with hydrophilic latex particles to mimic the behavior of viral particles. And it was not soil, it is a micromodel. A micromodel, a very simple example of it, is that if you take a glass plate, put a layer of glass beads on it, and put another glass plate on that, and seal all around it, and then put two holes on the two sides, now you have a network of pores. You can inject water and air and water with viruses or colloids, and the advantage is you can put it under microscope and see what is happening there. So that's what they did, and this is a photo from, this is sand, glass beads here, these four in the corners. There's water in the pores, and there is air bubble in the middle. And these are, as I said, fluorescent hydrospheres, and then you can see microspheres, and then you can see that they are all gathering at this air-water interface. So they proposed that this is the reason for this extra removal, attachment to air-water interface. And this was the thinking for almost 10 years, and then people started to question this, and they said, actually, this figure, this picture could be misleading, because true, if you look at a cross-section instead of a plan view, it's true that we have this air-water interface, here shown in blue, but we also have that air-water solid contact line over there. And if you look from this direction, you wouldn't know, are they really these on these red spots or on the blue spots? You will see the same thing. So in order to be able to see that, you really need to do confocal microscopy, which means that you have to look into the depth and focus at different depth in here. Then you can see where the viruses are. And I'll show you the work that we are doing exactly trying to do that. So other people did experiments, and here is one, for example, from Chris et al. These are glass beads. There is a pendular ring of water here, and so outside is air and there is water, and this is contact line between water, air, and solid. And they see that the colloids they are using, they are not viruses either, they are sitting at this air-water solid contact line. So that's also possible. Now, in fact, people have reported for the last 20 years or more, they have reported that we have attachment to solid water interface as the main reason for this extra removal, or attachment to the air-water interface reported by these. Some have reported, no, it's because of this extra attachment to the air-water solid contact line. And there are even those who have said that this is because of film straining and so forth. And what is interesting, these conflicting reports are given sometimes by the same person. Tork Saban saying the same, different things. And I must say he was my PhD student, which means that I can explain. And here is the explanation. This is the experimental setup that he had, a sand column of 20 centimeters. We did experiments both saturated and unsaturated, so we had tensiometers to measure and monitor the water metric potential. We had TDRs to measure water content. And we did two sets, actually we did a lot of experiments with PX174 and MS2. You may recall that this PX174 has a high isoelectric point, 6.6, and this is 3.9, is low. And then we did two sets of experiment. In one set, was pH either 7 or 9. At this pH, both of these are still negatively charged. And then we had saturation of 100% or 66% or 52%. As I said, during such experiment, all conditions are kept constant, and the only thing we change is to put in viruses and then discontinue with putting in viruses. The flow continues at these saturations and pH and so forth. In a second set of experiment, we went to a lower pH, and now at this pH, PX174 is positively charged. So you would expect that you will have a lot more adsorption of this to the sand grains. But what we did was the following. We added a phosphate buffer to the solution, and the phosphate adsorbed very strongly to sand grains, especially metal oxide patches, and therefore prevents adsorption of viruses to the sand grain. So basically masks the sand grain. So now if we do 100% saturation experiment, we shouldn't see any adsorption because the sand grain is masked, is buffered. And if we go to lower saturations and we do see very significant adsorption, then we know it is not because of the sand grain extra attachment to sand grain. And so that's what we did. We added this phosphate buffer and in this second set of experiment. I'm going to show you quickly results, one from each set. This is the first set, 66% saturation, and the pH analytic strengths are given here. And two viruses, as I said, or phages, MS2 and PX174. PX174 is hydrophilic, and MS2 is partially hydrophobic. That's why you see that PX174 comes out of adsorption much more than MS2 does. But at these pH values, we still don't have really a very strong adsorption. One other thing here we did is that we say if we model this data, so these curves, the solid line is the modeling result. If for modeling this, we need two-side kinetic adsorption model, that means we have adsorption both to solid and air. But if it is one-side kinetic, then we know it's only adsorption to the solid. So when you look at the results, one thing extra we did here, at this point, we changed the saturation. As I told you, everything was constant. Here, we drained the column. We changed the saturation from 66% to about 20%. And what happens, you see that you get these very large remobilization again. Viruses come out because we changed the saturation suddenly. So remember this was drainage. And if you look at the data, we see that there is not really strong adsorption. This is adsorption coefficient for PX174, and one side is what's enough. So we don't have adsorption to air-water interfaces in this case, whereas for MS2, we have some adsorption to the air. This is attachment coefficient for air, and also some to solid. And in fact, the coefficient increases when the saturation decreases. Then we went to the second set, and here is a pH of 6.2. But remember, we buffered the adsorption sites. We covered them with this phosphate buffer. So we see that at 100% saturation, there is very little adsorption. There is adsorption to the solid is very small, and there is no air, of course, because it's 100% saturation. But when we went to 70% and 50%, we got a large removal. You can see that from these. You can see the adsorption coefficient is very large, not to the solid, but to the air-water interface. So in this case, it is the air-water interface, indeed, responsible for extra removal under unsaturated conditions. Now, one thing we did extra here, this time, this is saturation of 50 or 7%, we resaturated the column. We put water back in. And this is opposite to drainage we did. And here we also have this extra, we have this very significant remobilization of viruses. They come out, instead of coming out very slowly, they come out in large numbers. So it's very interesting. Both drainage and imbibition will cause remobilization of viruses. Again, this is very important for field situations. In that river bank filtration I mentioned, when the river water all of a sudden goes up as a result of a flood, that means the bank will get resaturated. And viruses that were attached will come out of adsorption and get into the groundwater production wells. And in fact, water companies know that as soon as there is a flood in the river, they will discontinue taking water from their water systems. This is very important also if you are worried about colloid facilitate transport of pollutants, because what I just explained about viruses also happens to colloids, that they will get remobilized when you change the saturation of the water. So the question is, why is this happening? What is the mechanism for this remobilization? And in order to study that, we are doing Pore-scale visualization experiments using micromodels, actually. Our micromodels, here is a picture of it. These are network of pores that we have created, not using glass beads, but we have created in this network of pores in a material called PDMS. That is said here. The PDMS is a polymeric material. We create this network of pores, then we cover them with PDMS, and then this is 1 millimeter by 10 millimeter. We have 3 inlets, and there is an outlet, so we can put in water. We wanted to do experiments with water and air, but because we want to do confocal microscopy, we have to have 2 fluids which have the same index of refraction. So we couldn't use water and air. Instead, we use water and another liquid called fluorinert. They have the same index of refraction. So from these 3 inlets, we can saturate this, for example, with fluorinert. Then we put in water with colloids in there. And then we put in extra fluorinert, or we put in extra water in order to resaturate or drain this pore network. And then we look under microscope what is happening. This is our confocal laser microscope, and here is the micromodel and the 3 inlets, and there is the outlet there. I'm going to show you some results. This is a picture from a static conditions. There is no flow taking place. One of the first pictures we took. By the way, again here we didn't use viruses. we use the microspheres, 300 nanometer in size. They are fluorescent, so when you shine them with laser, you can see them, but of course you don't know where they are. So we turn on the lights and do optical microscopy. Now we can see this is the water, this is the fluoriner, and these are the solid surfaces. And when you superimpose these two pictures, now you can see that here the colloids are sitting at this contact line. You remember the fluid-fluid solid contact line. Majority of them are sitting here, some at the fluid-fluid interfaces, and the rest are in water. These are colloids that are hydrophilic, so they are introduced in water. Then we said, okay, what is the cause of this remobilization when we have saturation change? And our hypothesis, and there are other people who have proposed this, is that it's because of capillary forces, that these interfaces, when they move, they scour the walls of the pores and take with them these adsorbed colloids. So the question is that the case? What I'm showing you here is this is water with colloids. This is fluoriner outside of it. And then we inject fluoriner to cause the movement of this colloid. And see that there are lots of colloid adsorbed here, but as this interface moves, it carries all of them with it. There's nothing left behind on the walls of the micromodel. But then we said, okay, if this surface tension and capillary force is responsible to this, why not change that surface tension? See what happens. So, for example, reduce the surface tension. And that's what we did. We reduced the surface tension, and now we repeated the experiment. This is one of the same pores, actually. You see, first of all, there are colloids left behind, adsorbed. Here is water, here is fluoriner. They're adsorbed there. Then also when we move the interface, you see that here there are these colloids adsorbed. The interface, by the way, is flatter than the previous one. See, it removes some of them, but some stay behind. And so there are particles staying behind in adsorption, and this we believe, therefore, is because of. And so we are trying to model this. We also make measurements at the outlet reservoir, and we see indeed that we have the breakthrough curve. Well, the concentration goes up, and then at some point when we inject fluoriner, we see again a lot remobilization. We see the colloids coming out. These are like this picture was taken about 3 weeks ago, and we are continuing these experiments and hoping to provide a theory, quantitative theory, to model all this. So with that, I would like to end with the conclusions that the behavior of viruses and colloids in soil and groundwater is strongly dependent on hydraulic, hydrochemical, and environmental conditions, that generally there is enhanced removal under unsaturated conditions, and this could be due to one of the three mechanisms or a combination. That is either extra attachment to the solid water interface or attachment to air-water interface and air-water solid contact lines, and rapid changes in hydraulic and hydrochemical condition results in very significant remobilization of attached viruses. With that, I would be very happy to answer questions. Thank you. Thank you. Yes.
I thought it was interesting when you increased the ionic concentration by adding sodium chloride, you got that mobilization of viruses again. I live in a part of the country where we use a lot of road salt, and we get these big spikes in sodium chloride in our stream. So would that destabilize a riverbank filtration system?
I believe that if sodium has two effects. When you increase ionic strength, you will have more adsorption, because increase in ionic strength will cause that there's a diffusive double layer next to the solid. This will be compressed. The viruses, as if they get closer to the sand grain, and they can get adsorbed. What we did here was change of not sodium but calcium. The ionic strength remained constant here. And the only thing we did was to change a monovalent ion with a bivalent ion. So it's not exactly the same thing. In your situation, the ionic strength is low, and then it goes up. That could actually lead to even more adsorption. Other questions?
I've got one more, sorry. Early on, you talked about a standard of one virus per 5 cubic meters. We've been hearing in the United States that they're talking about having a few viruses in water is probably in the liter of water is probably okay because of the immune system. And what you're telling me, which always made me kind of nervous. So I'm just curious, where are you getting your factor that one virus per 5 cubic meters, and is that better than the language we've been hearing?
Oh, that's a few virus. I hope it's not per liter what you say is being acceptable, because that will definitely not be acceptable. As I said, the regulation is not based on concentration, based on the risk of getting sick. And these concentrations comes from a risk assessment study. It's a probabilistic study that has been done in an Institute for Public Health. I've not been involved there, so I don't know exactly how they have come up with these concentrations. But from what I understand, this 1 in 5 million liter is the concentration that corresponds to still allowing 1 person out of 10,000 people getting sick once a year.
My impression was that in practical applications, that when groundwater is artificially recharged and may have virus in it, that if it stays under the ground for 6 to 12 months before it's taken out, the virus dies. It's a time factor primarily. Is that something you find consistent with your research?
Yeah. So the first conclusion I had was that basically everything goes. Depends on conditions. But under average conditions, for example, in the groundwater systems in the Netherlands, there is a regulation that says 60 days of travel time is sufficient. So in determining the size of protection zones for drinking water wells, they say that the size of it is based on, of course it depends on the discharge they take from the wells, but the 60 days travel time. And this is originally coming from a microbiologist in Germany who determined this. And this is actually assuming that adsorption is not important. It's only based on inactivation. But we have done studies of more than 300 groundwater wells in the Netherlands and their geochemical conditions, and we have shown that 60 days is not enough. In some cases, you need a year.
Will these results be applicable to like bacteriological contamination too, like coli or coliform or?
Right. In fact, in our studies related to the safety assessment of these drinking water systems in the Netherlands, we don't look at bacteria because they are much larger than these viruses. If we can prove that the viruses have been removed adequately, the bacteria are somewhere from 50 to 100 times larger in size, and they will be definitely removed. Once again, it's different if you have a fractured system or you have heterogeneities involving gravel. Then you cannot say that anymore, of course.
You just said a year of travel time was better. That isn't really practical for a lot of riverbank filtration systems. Is that impacting their use?
For riverbank filtration, if the river, the formation of a bank is really fine to medium sand, then a couple of 100 meters is definitely sufficient. That is, I must say, once again, depends on if you, what the pH is and what the sand is itself. But the one year I mentioned is for certain groundwater wells. This is related to protection zone where the sand is very poor, for example, in oxide content, in metal oxide content. Then the adsorption is much lower, as I showed that earlier. Then those are the places that they have to look into it and have a much larger protection zone.
Does the attachment capacity of the sand and air and saturated system of the existing sand bank system you have, does that decrease over time? I mean, will this last forever? Does it get full?
Right, very good question. The dune systems I mentioned, I showed an aerial photo from Castricum. This is 100 years old. They have been doing this for 100 years to provide water to Amsterdam. And the answer is no, it will not fill up. And the reason is the following. The main reason for this system to work is not actually adsorption. Because if you only had adsorption and no inactivation, this is a system that is a steady state for many years. When you put in a given concentration into a column or here into the canals, after a steady state, the same concentration will come out as long as it's reversible adsorption. And this is all reversible adsorption. So adsorption enough will not do the trick. It is the inactivation that actually gets rid of the viruses. And what adsorption does, provides extra delay so that inactivation can do its work. So the viruses that are attached, as I said, they are being eaten up by bacteria and protozoa, and they disintegrate. So they are not there anyway. So it's not that they will fill up all the adsorption sites. They will die off. That is the way it works. Any questions? Guess we are done then. Thank you very much. Thank you.
Now, do we all feel a little bit better about drinking water now? Okay, I do. Okay. I'd like to thank Majid for an excellent presentation.
Thank you.
I think he's put my mind at ease. Next time I'm going to turn on the tap. So, once again, could we have one more round of applause?
Thank you very much.
Last lecture.
Thank you for your attention.
And reminder, if you're going to leave the room, as Kathy asked, please get scanned. Okay?